Okay, so in today's video, we're going to continue on where we left off the last one. In this one, we're going to go ahead and do the volume using the disk method. We're going to go ahead and see it through the washer method as well. So then we can go ahead and start off with an example. So the area bounded by the graphs of y equals 3x, x equals 9, and the x-axis is revolved about the given axis. Find the volume of the solid of revolutions. So we're going to revolve it around the y-axis, and B, we're going to revolve it around x equals -2. So to start this, we're going to start with A. Now if we go ahead and draw this out for part A, we know what x equals 9 is, which is just, let's just say this is 9. Here's going to be a line, right? And we know what y equals 3x looks like. Intercept of 0, 1, 2, 3, slope of 3, and our line is going to look something like this. And we know what the x-axis is, which is just y equals 0, which is this. So this is the area that's going to be revolved around the y-axis, like this. And it's going to create a 3D shape that's going to look something like this. Basically a cone in the inside. So the way we can go ahead and figure this out to find the volume, we know that volume, and if we go ahead and dissect this into small pieces, if we were to go ahead and look at a shape from here, right, dissect this, and pull this cross section out, our cross section is going to look like this, like a donut or a washer. We know that the volume, and this is a very small piece, right? We don't know really how small we cut it, but we know it's small. So then we know that since it's since it's perpendicular with the y-axis, we know it's going to be dy. And then we know that this is from A to B, and it is the area times the thickness. And now here we have two areas. We have a large circle, and we have a smaller circle inside of it that's cutting the area out of that. So we're going to have the area of the large radius minus the area of the small radius, which is going to be our actual area for this cross section. So our volume is going to equal from A to B, and the area, well, the area of a circle, we know that is pi r squared minus pi r squared. And I'm using the big R to represent the big radius and the little r to represent the small radius. So if we know what our area is, we know that it is pi big radius squared minus pi little radius squared. And our thickness, as we already discussed, was dy. Now, we have it in respect to y, but right now we have the variable of big R and little r. So we need to find a way to go ahead and relate that. Well, as you can see in this diagram, our big radius which is a circle on the outside, it never changes because x equals 9 and it's along this side. So we know that our big R is going to equal to 9 at all times. As we go higher, if we look at cross sections higher than what we did or lower than we did, and our big radius equals our large circle. Now, our small r is for our small circle, but as you can see here, our small circle's radius is changing as we go up it. The higher we go up, the radius seems to get longer. Now we know that our radius is x every single time, right? Because it's an x value. But the issue is we don't know what the value is. But what we do know is that it keeps changing compared to this line here. So if we know that our radius here, our radius is dependent on our x, our x, but we know that that line is y equals 3x. If we divide by 3 on both sides, we get y over 3 is equal to x. And if we know that r is equal to x and x is equal to y over 3, we know that r is equal to y over 3. And now we have it in respect to y. So if we plug that in, it'll eliminate our little r, and we can go ahead and have it in respect to y. So our volume from A to B, we can pull the pi out. We have our r squared minus little r squared with respect to dy. Now if we just plug that in, so our volume is equal from A to B, our pi, our big R we know is 9 squared, minus our little r we know is y over 3 squared dy. So now we don't have any other variable besides y in there. So we're good on that. But we still need to find what our a and b is. So our a and b, we're looking at it with respect to y. And we usually look at our original diagram first. So what is the height from here to here? Well, we know what this is. This is going to be 0. Right? This will be 0. And how about b, which is up here? The thing that we have there is we don't know how to find that. But what we do know is that the x is 9 here. So if this was a point, this point is going to be 9 comma something, because we're here on the x equals 9. If we can go ahead and figure out how that, we can figure that out by this line here. So if we were to plug in on y equals 3x, that x equals 9, we would go ahead and get that y equals 27. So we know that the height here is 927. So that means that our b is going to be 27. Now that we have on where we're looking at it from with respect, I mean, if we were looking at it from the x, if this was a dx problem, we would be looking at it from here to here. So we know that it would be from 0 to 9. But since we're not, we're looking at it from this area, from here to here, which we know is from 0 to 27. So if we go ahead and just plug this into our calculator, we're going to go ahead and get that our volume is equal to 1,458 pi. I usually leave it in terms of pi, comes out with a nicer number. If you need to go ahead and plug it in and find a decimal or a decimal place for it. Round to your nearest tenth, hundred, whatever it is. Go ahead and do so. So let's go ahead and move on to part B. We're going to go ahead and revolve it around x equals -2. So we have the same problem, but this time we're going to go ahead and revolve it around x equals 2, or x equals -2. We know that this is 9. We know that this is 27. And this is the area that we have. Now we know that -2 is here, right? This is -2. And that's what we have to go ahead and revolve it around. Now this is going to be kind of a concern. This is where a lot of people get mixed up on, is revolving it around something other than the y-axis or the x-axis. Because now we have a larger space here. We have this addition here. So the way we can go ahead and solve that is if you go ahead and actually only look at that, because we know that our volume is going to be almost the same formula, is going to be from A to B, and we're going to have our area of our big radius minus area of our small radius times thickness. But the thing is, now we're revolving around x minus 2. So our formulas for r's are going to be different. So let's look at this. If we look at our big R, right, from here to here, we know from here to here it's 9. And we know from here to here is 2 more. So we know that our big radius isn't equal to, and we know that this whole thing, well, here, right, is actually x. And we know that this was 2. We know that our big radius is equal to 2 plus x. Right? Graph got a little bit warped, so I'm going to draw that out. So that means that our big radius is equal to, but we know that our x here is actually 9, because it constantly stays like that. It's going to be 2 plus 9. So that's what our radius looks like. It's going to be 2 plus 9, which our radius is going to be 11. Now, if we go ahead and look at it here, which is here to here, as you can see, our radius changes for every single time we draw the cross section for our little r. So our little r is equal to, well, like I said, we know that that's 2. And we know that this part here is x, right? So it's going to be plus x. So how can we change our x to go ahead and define what that is? Well, we know that our x changes depending on this line here. And we know that that line is equal to y equals 3x. So if we divide by 3, our x equals y over 3. So we know that our r is actually going to be, r is equal to 2 plus y over 3. So we're going to put that back into our volume formula. Volume is equals from A to B, which we know that if we look at a cross section, I mean, we're bonding it, and if we look at it again, it's going to be like this. The only thing now is it's going to be, you're going to have a little bit of a base at the bottom, right? So then it's still going to look like a cone. It's not going to come to a point at the bottom. You're going to have a space of 2 there. So our volume, so when we look at our original diagram, it's going to be, when we're looking at it, the cross section from here, right? It's still going to be a circle. And we still know the thickness of this is still dy. So we have a to b. Now we know from our previous example, we could pull out a pi. We're going to have r squared, which is our big radius, minus our little radius, times our thickness, which is dy. So we have our volume is equal from a to b, which is going to be a to b of pi, our big radius to be 11 squared minus 2 plus y over 3 squared dy. And like I said before, we're looking at it with respect to y. So if we know what the bottom is, according to our graph, which should be 0, and we looked at this one, and we know that this one was 9 on the x-axis, we know that this is going to be 27 again. So what we're going to do is we're going to go ahead and have it go from 0 to 27 pi of 11 squared minus 2 plus y over 3 squared dy. Now, if we go ahead and plug this into our calculator, and my calculator has an integration button, I'm going to put 11 squared minus parentheses 2 plus y over 3 close the parentheses squared close the parentheses again between 0 to 27. That should give us, oh, I forgot to include the pi. Don't forget to include the pi. That'll give you a totally different number, and it will mark it wrong every single time. That'll give me 1,944 pi. So that's how we can go ahead and solve the volume of this 3D shape when we rotate it about x equals -2. So those two methods were really the washer method or dish method or whatever you prefer. Now let's go ahead and look at the first problem where we rotated it along the y-axis, and let's look at it through the shell method. Okay, so if we go back to this problem, and if we rotate it around like how we did earlier, the y-axis, we're going to get this kind of shape here, which was basically a cylinder with a cone or cut out cone inside the middle. So if we have this shape and we decide to use the shell method, all we're doing is we're going to go ahead and draw from point to point a cylinder. And basically it's like grabbing a sheet of paper, a thin sheet of paper, and converting it into a circle. Well, if we bring this out and we unfold it, unfold this sheet of paper that we're considering a cylinder or a shell, what we're going to do is we're going to get a piece of paper. And this piece of paper has a piece of thickness, which we don't know what it is, but we know since this thickness is lying here, it's going to be the X. So it depends. You can use like previously we used this method and we got a dy. If that's easier for you, use that one. Some people prefer it to be in respect to X. So if you prefer it to be in respect to X, sometimes you might need to do the shell method. So here we know that this is just a width, right? And this is just a height. So if we look at this cylinder, we know that here's the center. And this here is our radius. But as we go higher and higher and higher, our radius for our shells are going to keep changing, right? So we know that our radius is equal to an X value. Because if you come down here, it equals that value, equals that value, equals that value. And that just means our shells are getting bigger and bigger and bigger. And our radius is here. So if we know that our height is dictated by this graph here though, right? Because our height goes from here to here to here to here. So we know our height is dictated by 3x, or y equals 3x. Or what we can say to start off is our height is dictated by the y value, right? Which will be this value here, this value here, this value here, this value here. So these are all our heights from our different shells, and they're dictated by these y values. So if we know what y is, which is this line here, y is equal to 3x, and we know where our h is equal to y, our h is equal to 3x. We're just plugging in h in for the y. So now that we have those, we can go ahead and start with our volume. Okay, so to find the volume of this, we know that it is usually its area times the thickness. Well, W, we don't really know what W is yet, but what we do know of it is that if we were to take this sheet of paper, I'm just going to draw it in a simple form, which is usually a straight line, which is W, and we grab this and we turn it into a circle, it started from one point and ended from another point. So this length here started here and it went around is the same length as here that goes to here. So this is also our W, which our W is equal, let me write this differently, is equal to the circumference of the circle, another circle that we created. So if we know what the circumference of the circle is, circumference is equal to 2 pi r, we can go ahead and figure this out. So if the volume from an interval from A to B is the circumference times the height times the thickness. And the circumference would dictate that the circumference and the height would be basically our area of that piece of paper, which is just W times height, because our area for this piece of paper is width times height. And then if we want to find the volume of it, it's volume is equal to width times height times thickness. So we know that this is the area, which is W times H, and our volume is going to be W times H times thickness. So our volume between A to B, W, H, thickness. So now that we know that W is equal to 2 pi r, our volume from A to B, our W is 2 pi r. Our H, we know it to be Y, because that's what we found out here earlier. And our thickness is dx. So the problem we have right now is we have two other variables that are not in respect to x. So we know that our h is equal to y, but we know what our y is equal to. Our y is equal to 3x. And we found that out here, that our h was actually 3x. So if we substitute our h there instead of the y, we would find that it was 3x here. So that's fine. We found what our h or our y was with respect to x. But now we need to know what our radius is. Well, we know that our radius is equal to x, right? And our radius, being that it's equal to x, and is determined by this graph here. Oops, sorry about that. Our radius is dictated by this graph here, or that line, per se, which is y equals 3x. We can go ahead and manipulate y equals 3x to get what x equals, which equals y over 3. All I did there was divide both sides by 3, and I got x equals y over 3. Right. So that's what our x is equal to. Sorry. I apologize. Our x is not equal to y over 3. Our x is going to be an x value every single time. So we found out that's what r is equal to. It's just a different x every single time. So in this case, our volume is equal to A to B of 2 pi. We know that r is equal to an x value at that moment in time times x with respect to x. So we already found out what x was here. We don't need this. So our volume, now that we have everything in respect to x, we can go ahead and simplify this, which is going to give us 6 pi x squared dx, our integral between a to b, and since these are in respect to x, like I stated earlier, it's respect to x now, we need to know what this value is here and what this value is there. And we know that this is here, 0, and we know that this is 9, because that was the line of x equals 9. So we know that our bottom, our a, is going to be 0, and our top is going to be 9. So our volume, using the shell method, is 1,458 pi, which, if you remember, it should equal the same value that we got for our dish method. So there's just two different ways that you can go ahead and solve this. Neither one is more or less correct. Some can be simpler than others, but this one's doing the dish method or washer method, and this is doing the shell method. One point to take away, and something that I get confused with every now and then, is that R is equal to X. Majority of the time, your R is going to be equal to whatever you're respecting to. In this case, we're respecting to dx, so our R is going to be dictated by an X value. And that's because our R here is X, our R here is another X, our R here is another X. And the thing is, that's how it's usually going to be when you're using the shell method. So whenever you have your R, which is your radius, it's going to be dictated by whatever your X value is at that position or at that specific drawing or that specific shell. So that's how you can kind of use these two methods. This one's the shell method, and the previous one was the disk or washer method. And we'll look at some other problems in the next video about another section.